In this demo, I'm going to use the gradient descent is the most used function to monitor and to optimize the model.
We have seen how the cost function evaluates how well model perform by using data. The optimizer is the final piece of the puzzle. The role of the optimizer is to alter the model in a way that improves its performance. It does this way by inspecting the model output and cost and suggesting a new parameter for a model. For example, in our framing scenario, our line model has two parameters. The line is intercept and the line slope. If the intercept of this line is wrong, the model will underestimate or overestimate temperature on average. In this slope is still wrong. The model wants to do a job to demonstrate how temperature have changed since the start date. The optimizer change these two parameters so they don't have optimal job to modeling the temperature over time. A gradient descent, the most common optimization algorithm today, this algorithm. Several variants of the algorithm exist, but they all use the same core concept. Gradient descent use calculus to estimate how changing its parameter will change for the cost. For example, increasing parameter may be predicted to reduce the cost. Gradient descent is named such as because it calculates the gradient slope for the relationship between each model, parameter and a cost. The parameters are then altered to move down this slope. This algorithm is simple and powerful, yet isn't guaranteed to find the optimal model parameter that minimize the cost. The two main sources of the error are locally minima and interceptability. A local minima, our previous example looked to do a good job, assuming the cost would have kept increase when the parameter was smaller than 0 and greater than 10, like show this example, smaller than 0 and greater than 10. This wouldn't have been such a great job. If a parameter smaller than 0 or larger than 10, we would have a result in lower cost like this image. In this graph, a parameter value of -7 would have been a better solution than 5 because it has a lower cost. Gradient descent doesn't know the full relationship between each parameter and the cost, which is represented by the dotted line in the advance. So it's prone to finding local minimal parameter estimates that aren't the best solution, but the gradient is 0. Instability are related issue is that gradient descent sometimes show instability. This instability usually occurs when the step size or length vary. The amount that each parameter is adjusted by each iteration is too large. Parameters are then adjusted too far on each step, and the model actually gets worse with each iteration, like you see in this first image. Having a slower learning rate can solve the problem, but might also introduce issue. First, slower learning rate can mean training take a long time because more steps are required. Second, taking a small step make it more likely that training settle on a local minimum, like the second graph. By contrast, a faster learning rate can make it easier to avoid hitting local minimum because larger step can skip over local minimum, like the final image.